Welcome back to our System Dynamics and Vibrations video lecture series. In this video, we're going to be talking about electrical circuits and motors, and we're going to eventually show that the mathematical analysis and mathematical tools that we've been using for physical systems and mass spring damper systems also apply to electrical systems. Um, so, bit of a brief introduction to electricity. We're going to be talking about a couple different quantities. The first one is current, and the current is a measure of the flow of electrons through a circuit. Um, and so it's measured in amps, um, and an amp is 1 coulomb per second, which means and a coulomb is really just a number of electrons. It's approximately 6.24 times 10 to the 18th electrons per second. And so if we think about electricity and electricity flowing through a wire similar to um, some sort of fluid or water flowing through a pipe, then current is the same measure as a gallon per second or milliliters per second. It's just measured in electrons flowing through a wire. Um, we also have a voltage. And voltage, if if current is a flow per second, voltage is more of a pressure. So it's an electrical potential um, across some element. So if we have in our pipe, if we have some high pressure on one end and some low pressure on the other end, that's going to cause the fluid to flow in this direction um, to try and equalize the pressure. And the pressure differential delta P is um, going to have a large. It's going to factor into how much flow is going through. Um, so in that power, and that's analogous to power. So in a mechanical system, um, power is equal to a force times a velocity. And in an electrical system, it's equal to the voltage times the current I. So we have these analogies that kind of help us as mechanical engineers think about electrical systems. And that's kind of the level that we'll need to be thinking about electrical systems and electrical ideas for this class. And so we're going to be talking about three different passive elements of electrical circuits. The first is a resistor. Um, and a resistor, it's drawn kind of like a zigzag line. And a resistor is going to have some current IR going through it, and there's going to be some voltage or some pressure on one side and some voltage on the other side. And so you'll often see uh, that the relationship for current is that let's do voltage first. The voltage, sometimes you'll hear it said of a resistor is equal to I times R, or the resistance, which is measured in ohms. And what that really means is that the difference, VA minus VB is equal to the current passing through that resistor times the resistance. You can also write that as the current is equal to some V over R. And again, that's the difference, the voltage across the resistor that we're measuring. So VA minus VB over R. We also have inductors, which are kind of drawn like a spring, like a coil. It's fundamentally a coiled wire. And the current through an inductor is equal, so it has an integral, so we've got some initial position, or some initial current plus 1 over L, which is the inductance, times the integral of the voltage of tau d tau. And this is an integral to V of tau, and we'll put some limits on this. Tau equals T0 to T. The voltage is the difference from one end to the other, from one end here to the other end. So it's the integral of the difference in voltage over the system. We can rewrite this as some integral of VA minus VB d tau. And we can rewrite that as well, that the voltage change across the inductor is equal to L times the derivative of current. And finally, we have capacitors, drawn like this, with a capacitance C, and the unit is a farad, spelled like that. And the current going through an inductor is equal to C times dV dt. Again, that's the rate of change of the difference in voltage of a delta V. And V is equal to, similarly to the inductor, we switch which one's a derivative and an integral. V of T0 plus 1 over C times the integral from tau equals T0 to tau equals T of the current I as a function of tau d tau. And so when we're starting to look at the integrals and derivatives, if we start to add these up, oops, integrals and derivatives means we're dealing with differential equations. We're dealing with first or maybe second order differential equations, and that's where some of these analytical tools that we've already been discussing are going to come in.